Hello everyone, I hope you can hear my voice properly. Let me rearrange that a little bit. Okay, we are going to be talking about chapter 2, which is limits and continuity. There's a part that I skipped last time, and then we are going to start at that point and then continue from here. From now on, actually, we are going to follow Thomas's book. The reason is I have realized that the lecture notes are much better to follow, and also we have the online work resources that I was able to get from the publisher for you for free. So we are going to use that. These resources are going to be for free only during the COVID-19 period, by the way. It may not go on like this in the fall, for example. Okay. Alright, so we are going to, let me double check the recording. Alright, so let's see what we have for the limits and continuity. We are going to talk about the rates of change and tangents lines to the curve. Let's see, so this was the part that I skipped last time. I said that we would come back again. So speed, velocity, these type of terms actually calculus was at the very beginning very interested in. So that's how actually calculus evolved, you can say. So these are main problems in calculus. We have to touch them, we have to talk about them, and we use them in physics and everywhere else. So what's an average speed? Let's give a definition of that, okay? So let's say an object is traveling, started to travel from time t1 to t2, and we are interested in the speed of that. Of course, the object is traveling. This could be a car. Let's say a car is traveling, and this car may change the speed time to time while traveling. So we are interested in the average speed of that car. How do we do that? How do we find the average speed of the car? Average speed of the car on the interval time t1 to time t2 is going to be the you're going to look at the distance traveled, the total distance traveled, divide this by the time that passed during that time, which is t2 minus t1. The distance traveled can be found. We have a function f of t. F of t is the function that measures the distance traveled at time t. So for example, f of t2 is the distance traveled at time t2, okay? For example, f of t1 is the distance traveled at time t1. So if you take the difference between the two, this is going to tell us how long did this car traveled in the time interval t1 to t2. We take this ratio, and this is going to give us the average speed of the car, okay? Of course, there are some notations that I want to introduce you. Just a sec. There's a problem with the recording for some reason. Alright, so so how are we gonna, so there are some terminology, of course. Average speed. The time interval time to time is shown as follows. T0 is the time that we start, and t0 plus h, h is the period that has passed, okay? So the average speed on this interval is going to be delta y. Delta y is the distance traveled, delta t is the time passed, okay? The function in here is, actually this is coming from the example, the function we are given is 16t squared, okay? So we want to find the average speed, f of t. Let me try to write it here. Hopefully we will do that. Just a sec, give it a try. let's see if it's gonna allow me to do that. There's just a little bit of things that's going on. I wanted to open up and write in here. It doesn't allow me, so that's fine. We have to open up the whiteboard to write it, so it's not gonna allow me to write it, so no problem. That's okay. Alright, so what I want to say, so you will just listen to me and try to follow the cursor to understand. That's the only way we could do right now. I don't have a better way. Just a sec. Okay, come on. Okay, so this is just a table. This table tells us, for example, whenever the time interval is 1, we calculate the average speed when the function is f of t is equal to 16t squared. Okay, and then we are assuming that, let me check the recording again. So recording caused the problem. Okay, anyways, if it doesn't allow me, I will find other ways to record it, okay? I have other ways to record it. So I'm actually recording by using two softwares. So since this doesn't allow me to record, I will send you the other copy. Thank God I do that. Okay, so sometimes these things happen. No problem, no worries. We have always a backup. Okay. All right. So so the time interval h could be 1 minute or 1 hour. I mean, I think this should be in terms of minute. Short interval we are talking. 0.1 minute. You can have the second as well. We have to see the question. Let's take it seconds, okay? 1 second, 0.1 second, 0.01 second. These are the time interval it passes. And then we just calculate the average speed by using this delta y over delta t. Okay? This is the average speed. As you look into this, as the time interval gets smaller and smaller, average speed drops down to 32. Okay? This is actually, there's a difference between this and this. This is when we start at time t0 is equal to 1. And this is going to start at time t0 equals to 2. If you look at the average speed and if you just decrease the time interval to a very small amount, this is going to give you the actual instantaneous velocity. Okay? Anlık hız. Okay? Just anlık hız in Turkish. Instantaneous velocity. So this is, how should we read this? For example, at time t is equal to 1, the instantaneous velocity of this car is around 32. Okay? On the other hand, at time t is equal to 2, the instantaneous velocity is around 64. Okay? These are all average velocities, but we take the limit. We make it smaller and smaller interval. So this is so that we get the instantaneous velocity. That's the goal in calculus. Average speed are good, but that's not the best thing. We want anlık hız, yani o andaki hız. What's the instantaneous velocity? We want to know that. Okay. Therefore, we do that in such type of tables. Okay, we are going to do this in limit theory as well. Average rate of change of y is equal to f of x with respect to x over the interval x1, x2. Now, we just talked about the average speed. Now we can extend this notion to a general notion, which is average rate of change, okay, of y, of a certain function y. So this, you can apply this definition to any category, like not only the speed category, you can apply it to anything in economics, in biology. That's why we need this general terminology definition, the average rate of change. What is that? This is when you're going to be given a function. That function is going to represent a certain information, okay, and then in the speed case it's the displacement, change of location, but for this function it could be something else, right? It could be the height of girls, okay, at some certain times, at age 1, age 2, age 3, age 4, etc. And you can just calculate the average rate of change in girl's height, maybe, okay? So anything it could be. And the formulation, you see, it's similar. Delta y over delta x. We have the f of x function that's given. We are interested in the interval. This could be time interval. This could be some other interval that we are interested in. And then f of x2 minus f of x1 over x2 minus x1. We can write the same definition differently. If we know that the time interval, the length of this time interval is h, then we can write the same thing as f of x1 plus h minus f of x1 over h. H is not going to be 0. So there are two different ways to write the same thing. Alright, so, okay, let's go back to geometry. So let's say the function that we just talked about is f, and we talked about the average rate of, let's go back to it. No. Okay, we talked about the average rate, and first we talked about average speed and average rate, okay, here. And when you look at this function, geometrically, what does this mean? We want to understand it. So we write delta y over delta x, right, as the average rate of change. Delta y is the, okay, so this is the interval that we are interested in, x1 to x2. And we look at the corresponding f of x2 and f of x1. And we have delta y here, delta x here. Delta y is f of x2 minus f of x1. Delta x here, x2 minus x1. And then if you look at the delta y over delta x, you are going to get the slope of the secant line. So we call this line combining these 2 points. Okay, we have the point P1, Px1, f of x1, and we have the point Q, x2, f of x2. If you combine these 2 points, you get a secant line. Okay, actually this delta y over delta x is nothing but it is the slope of the secant line. Alright, okay. So in other words, the average rate of change of f over the interval x1 and x2 is the slope of the secant line. Okay, it's good to keep in mind because it's going to be useful. Okay. Okay, and then let's continue. Last time we talked about the tangent line to a circle. A tangent line is going to be passing through this circle at one point, and we call it tangent line to the circle L, and this line is going to be perpendicular to this radius here. Okay, just give me 1 sec. Okay. I hope you can hear this music as well, soothing music. I hope you're gonna be okay with that while you're listening to me. Okay, so let's continue from here. We talked about the tangent line to the circle here. Okay. As you see, if you consider the center of the circle, and if you draw this line, this is a radius, and this radius has to be perpendicular to this tangent line. Okay, we have this perpendicular angle here, like 90 degrees angle here, right? Alright, so let's see the next one. Next page. I'm reading. Okay, so what should we understand? So these pictures, these graphs, etc. are much better in Thomas's book. And you're gonna understand them a lot better. So let's see. So let's say this blue color, this is a curve, and we fix a point P on the curve, and we draw the red tangent line to this curve at this point P. Okay, and then so our goal is always try to find the slope of this tangent line. I talked to you about this in our last class, so I'm going to repeat again. So how are we going to find the slope of this tangent line to the curve? Okay, this is what the calculus actually worked on many years in ancient times, right? In a long time ago, when calculus was being built. And the solution to this was looking at the secant lines. And see, for example, we choose another point Q on the curve, and then we get this point Q closer and closer to P, and each time we draw a secant line, and you should agree that finding the slope of a secant line is easy, because we know this point Q, we know this point P, and the tangent to the curve, when you know 2 points available, is very easy, y2 minus y1 over x2 minus x1, right? As long as you know these 2 points, the coordinates. And of course we assume that we know them. And then as you get closer to the P, you choose another Q, here there's another Q here, another Q, and each time you draw these secant lines. And these secant lines are getting, as you see, they are getting closer and closer to the tangent line. So you're approximating tangent line slope by using the slopes of these secant lines. Okay, see, these secant lines are going towards this tangent line. Okay, so in other words, as Q approaches P, look at this notation, as Q approaches P from one side, from right, the slopes of the secant lines, you calculate the slope of each secant line, and you're going to see they are going to get close to the slope of the tangent line. That's the idea. So you're approaching to P from one side, from the right side. Can you do this from the left hand side? Yes, you can. So choose a point Q to the left of P. This Q is on the right, right? Choose a point Q on the left of P. Here, Q on the left of P. And then you get closer to P from the left. And again, what you do is you just build up, draw these secant lines, and these secant lines, of course, have slopes. You can calculate them, and then look at where these slopes go to as Q approaches to P from the left, and the number that you get to is the slope of the tangent line. That's how people in old times calculated the slope of the tangent line, because they don't have anything else in hand. Okay, they don't have computers or anything. Anyways, on computers they have this idea too. Okay, the idea matters. If you have the idea, then you can do it. Okay, so that's how they did it. Okay, there's a question. Find the slope of the parabola y is equal to x squared at the point 2, 4 as limits of secant slopes. This is an example 3 in the book. Okay, so how do you do that? Okay, what you do, at 2 we have the point P, and then we are going to start writing our Q's. Fix at point 2 plus h is just the distance between delta x is equal to h, okay? It's just h interval. And then you just a sec, something is happening. Okay, and then you find the q, the value of this point q at this 2 plus h. How would you do that? We have the function, right? F of x is equal to x squared, so we put it in. At x squared, 2 plus h squared is here. So this is f of 2 plus h minus f of 2 over h. Okay, this is the second slope of the second line. Okay, h plus 4. So, of course, this is delta x is h. As h goes to 0 means this q is going to get closer and closer to p. So if we let h goes to 0 here, we are going to see that the slope of the tangent line is 4. Okay. Of course, later on, when you learn the differentiation, you will be able to take the derivative of this y is equal to x squared, which is 2 times x, and put 2 in here, you get 4. So this, this is easier, of course, but you have to know where all this come from. And these are the background, okay? This is where we get them. Alright, so let's continue on. Okay, so I'm going to skip that, it's similar. So here they are interested in finding the slope at a point as well. So they just build the secant lines from the right, and they look at, they calculate the slope of the secant lines, as you see, and see they get closer to, look, the interval is getting closer, smaller and smaller. The point Q, actually, look at the point Q, we are interested in point P, right, which is 23. So here, so we are getting closer to the point 23, but this is 30, right? 45, 40, 35, 30. So we are getting closer to it. And we look at the slopes. The slope is increasing, right? Because these secant lines have less slope, and as you go towards the left, they are getting bigger. So we are assuming that the slope of the tangent line at P is close to 16, right? If you do more, like if you choose some other points, like instead of 30, maybe you can choose 25, you're going to see you're going to get a better number there, okay? Okay, so now next, what we have seen is actually they prepared us for the notion of limits. In section 2.2, we are going to talk about the limit of a function and limit laws. So let's get this example. This f is x squared minus 1 over x minus 1, right? So I want you to just concentrate on the first graph. So look at this graph. This is just a line where one point is missing here. Do you see that? Why do we have this missing point in here? Because if you look at the denominator becomes 0 at x is equal to 1. So this is a bad point. So this 1 is a bad point. So since it's a bad point, we have to keep it open because the function is not defined there. But next, what I'm going to do, I am going to define it. Just a sec, let me. I want this to go away, by the way. Okay. So this next example is, it says you can actually fill this in by defining a new function. Okay, so I'm going to define, or you can say, I'm so sorry, look at this function again. You can factor this out. This is x minus 1, x plus 1, and then you can cancel x minus 1s and you get x plus 1. Actually, this function we have here is almost the same as the regular line we have, except one point. They just don't agree at this one point. Just one sec. Okay. As I told you, we have this line and we have the top function. They are exactly everywhere except x is equal to 1. Okay, do you see that? Okay, so in the first one, what's the difference? First function is not defined at 1. Second function is defined everywhere. Okay, let's try to analyze this function f of x squared minus 1 over x minus 1 a little bit closer. We are going to build a table, because whenever we don't know much about a function, we build a table. We want to understand, and also we want to see what happens as x gets closer to 1. Okay. So we just choose some numbers that's close to 1, 0.9, 1.1, 0.99, 1.01. This is less than 1, this is bigger than 1, this is less than 1, this is bigger than 1, less than 1, bigger than 1, less than 1, bigger than 1, but these are getting very close to 1. Okay, so then we just put it in here. Of course, we use a calculator or our computer to get these numbers. As you see, as x gets very close to 1, the value of the function is actually getting to 2. So this really agrees with the previous slide. So as x approaches to 1 from the right and from the left, the function is getting close to 2. Look at that, this height and this height. Okay, so this table also confirms us that this is the case. Let's see. Is this the end? Let's see. Okay, we studied this example. Okay, I'm waiting this to get come out again. Here's my 15. Okay, I'm going to share again. There's a problem, I believe. Okay, so we are back again, and now I want you to look at these three functions. Okay, so this function, you know, part C, it's a line, x plus 1, and this function we just talked about, this is almost like this function except 1, because at 1 there's this denominator that causes a problem. And this is the third function. This function is actually we use this function, and then we just define this function at 1, because this is not defined at 1. This is defined everywhere. So this function is the function that we get after we fill in at x is equal to 1, we define it as 1. So whenever x is not 1, g is x squared minus 1 over x minus 1. Whenever x is 1, we want to define it at 1. Okay, we just choose it. You can define as 15 or 100, whatever you want. Okay, just fill it in. So now this function is defined everywhere, and this function is defined everywhere. Okay, and all these three functions differ only at x is equal to 1. This function is not defined at x is equal to 1. Okay, now let's look at the limits. By limits we mean we look at from the right and from the left as x approaches to 1. So we are going to look at the height of this function line to the right and to the left. It is 2. And similarly, the limit is 2 from the right and left. And here the limit is 2 from the right and left of 1. So as x approaches to 1, all these three functions have the same limit, but they are not the same functions, by the way, okay? Alright, so these are all continuous functions, identity function and constant function. These are all continuous, so there are no stopping or jumps or anything in here. We are going to talk about them too. Look at this. These are the examples where we don't have limits at x is equal to as x approaches to 0. Look at that. So for example, this function is defined as follows. Whenever x is less than 0, it is 0. Whenever x is greater than 0, it is all 1. At x is equal to 0, it is defined as 1. So this function is defined everywhere. Okay, this function is defined all on all real line. But at x is equal to 0, I'm interested in the limits. If I get close to 0 from the right, look at the height, it is 1. If I get close to 0 from the left, the height is just 0. So the heights from the right and from the left, they don't match. Whenever you have that, we have a jump. If there's a jump, then we don't have a limit in there, okay? So there's no limit as x approaches to 0 here. So if you look at this example, part B, it's 0. So if you look at from the right and we look at from the left, if you approach to 0 from the right, look at the limit where it goes to. It goes to the value of the function goes to infinity, plus infinity. Okay, and when we look at from the left, the function gets very small and it goes to negative infinity. So if you look at from the right and from the left, they are infinite values. So because of that, the limit doesn't exist. We call this actually infinite limit. Okay. And then here, for this f, if you look at from the right, from the left, the limit is 0. And from the right, look at this function. This is an oscillating function, sine 1 over x. This is a famous function, sine 1 over x. Whenever x is greater than 0, sine 1 over x, as x approaches to 0, it oscillates, goes up and down between negative 1 and 1, never stops. We don't see it, but this is like never stops. So as x approaches to 0 from the right, there's no way there's a limit because it doesn't stop. It just gets to close to 1, goes down to negative 1. So there's no just single value that it's getting close to. So because of that, because this function is oscillating, we call it oscillating or oscillating. Okay. So let me write that as well. Maybe I should write it here. If I can write it in the chat. Okay. For C, we call it oscillating function. Oscillating function. It goes up and down. Okay. Because of that, it's not at all. So it's not. It doesn't have a limit. Okay. So these were the examples of functions that which there's no value, there's no limit as x approaches to 0. Okay, so next, let's see what's next. Okay, so next we want to talk about the limit laws. We are talking about limits, so there should be some laws that comes with it. Okay, theorem 1 states all these laws. So let's say we have, let's assume that f and g are two functions where we have limits. For f, if x approaches to c, it is l. Whenever for g, the limit as x approaches to c, the limit is m. So what happens if we add them up, f and g? The limit, what's going to happen to the limit? It's the sum of the limits. If we take the difference between these two functions, what happens to the limit? It's the difference of the limits. If you multiply the function f with a constant k, you get a new function. What's the limit of this new function as x approaches to c? It's k times l. if we multiply f and g together and look at the limit as x approaches to c, what happens to the limit? It's L times m. If we take the ratio of f and g, what happens to the limit? It's the ratio of the limits. But we have to be careful that limit of g is, this m is never 0, because otherwise it makes the denominator undefined of this expression. If I take the nth power of f and then take the limit of that new function as x approaches to see, what happens to the limit? It's just the power of the limit L, okay, L to the n. N is a positive number, integer we assume. And then we have the root rule. Let's say we have a function f and we take the nth root of that. What happens to the limit? It's the limit is nth root of L. Okay, we assume this n is when n is a positive integer, by the way. Okay, what happens if n is even? If n is even, we assume that f is a positive, greater or equal to 0. Otherwise, it doesn't make sense, right? For example, square root of -1 doesn't make sense for us. So this n is a positive integer, but if n is positive, we assume f to be greater or equal to 0 function. Alright, these are the rules. When we have polynomials behave really nicely. Polynomials are nice functions, okay? And the limits are going to be very nice as well. So what's the limit of a polynomial? This polynomial is a n x to the n plus a n minus 1 x to the n minus 1 plus a 0. What's the degree of this polynomial? The degree is n. And what's the limit of this polynomial as x approaches to c? It is very easy. It's just you put it in the c value, p of c, and then you get the result. So it's very simple. When you have a polynomial, you just put it in, the value, and you get an answer. But for the rational functions, that's not the same story. For the rational functions, we have to be a little bit more careful. Rational function means it's the polynomial over polynomial. Let's say p and q are given polynomials. And let's say q of c is not 0. So we assume that here, q of c is not 0. So the limit of the rational function as x approaches to c is just p of c over q of c, as long as q of c is not 0. So it's a nice situation as well. Let's give some examples. Let's say we have the function. Look, this is a rational function because polynomial over polynomial. X squared plus x minus 2 is a polynomial over x squared minus x is a polynomial. Polynomial over polynomial. When you draw this, actually, of course, right now you don't know how to draw them, but like at the end of the semester, you will be able to. At the end of the summer semester, you'll be able to draw them by hand. What happens as x approaches to 1 for this function? At x is equal to 1, by the way, the limit doesn't exist. I mean, the value of the function doesn't exist because at x is equal to 1, the denominator becomes 0. It's a bad point. 1's a bad point. But we are interested in the limit. What's the limit? So we look at from the right and from the left. Look at the graph. The graph is in front of us, so we can just make use of it. So the limit as x approaches to 0 from the right and the left, it is 3. So that's nice. Look, if you factor this out, x squared plus x minus 2, if you factor it out, you're going to get x plus 2 times x minus 1 on top. And if you factor out x squared minus 1 minus x, you get x times x minus 1. If you simplify the x minus 1's from here, you get this function left, x plus 2 over x, okay? So actually this function and this function are almost the same except one point, at x is equal to 1, okay? And the question is, what is the limit? As x approaches to 1 from the right and from the left, it's just the same, which is 3, okay? This is a function that's not defined at 1, but this is a function that's defined at 1. Okay? Alright. So let's say we have an example which contains the rational function, root function, I should say. So this is the root function, square root of x squared plus 100 minus 10 over x squared. And we want to compute the values of f of x near x is equal to 0. You can consider this as the function is square root of x squared plus 100, and then you are interested in finding the slope, which is f of x plus h minus f of x over h, right? Or f of yeah, that's what it is actually here. So you just choose some points close to 0. So plus n minus 1, plus n minus 0.5, plus n minus 0.1, plus n minus 0.001, etc. If you continue like that. You look at the corresponding f values. You put all these values in, and you get these values. Okay, so look at these values. These values, if you stop here and just take a look. Just stop here and take a look at the first 4. Look at that. So it seems like it gets close to 0.05. Okay. These values get close to that value. But if you continue further, like if you get more closer to 0 by picking closer values to 0, look at that. The computation shows you that you get very, very small values. Actually, you get zeros. So we are going to say the limit is going to approach, this is actually rate of change you can consider, right? Like this is f of x2 minus f of x1 over x2 minus x1. This is when f is square root of x squared plus 100. Okay, average rate of change here. Okay, so we get the limit as 0. So the instantaneous velocity, if you can think of this in terms of the velocity, the instantaneous velocity at x is equal to 0 is 0. Okay, you can say that. Next, we will talk about the sandwich theorem. Sandwich theorem is really an important theorem. It helps us to find limits by using the limits of other functions. Let me try to explain this picture to you. Let's say we are interested in finding the limit of this function f, this weird function f here, the blue one. But we don't have, let's say, a lot of information about f, but we know some functions that are bigger than f and smaller than f, and we call them h and g. And let's say this function f is squeezed between the top function h and bottom function g around c. And then the sandwich theorem says if you want to find the limit of f as x approaches to c, you just look at the limit as x approaches to c for h and g, and they have to agree. They all have the same limit around c, because f is squeezed between h and g. We sometimes call it squeeze theorem as well. Sandwich theorem, squeeze theorem. Okay, so in Thomas's calculus it's called sandwich theorem. Squeeze theorem, you can see that as well. So here we have 3 functions, g, h, g, f, h, and they are all they are ordered like this on some open interval, and this interval contains the number c. Okay, and then let's say we know the limit of g as x approaches to c, and let's say we know the limit of h as x approaches to c, and it is L. Then the limit of the function in between, that's in between, is going to be the same limit, L. Okay, this is sandwich theorem. Let's give an example. Let's say we have a function u, and it's squeezed between 1 plus x squared over 2 and 1 minus x squared over 4. Okay? The question is, what's the limit of this function u as x approaches to 0? Okay? So let's find the limit of this as x approaches to 0. So this is just a polynomial. So the limit of this is going to be just put 0 in. So 1 plus 0 over 2, 1. So the limit is 1. And let's look at this. This is a polynomial too. And look at the limit, just put the x is equal to 0 in. 1 minus 0, it is 1. And from the top and bottom, the limit is 1. So we are going to say the limit, any function that's in between these two functions, is they are going to have the same limit as x approaches to 0. Okay? So that's nice. We have two more examples here. Sine theta. The blue one is sine theta. By the way, sine theta is between negative theta and theta all the time. Okay? This is a fact. And by using that, as x approaches to 0, what is the limit of sine theta? Then sine theta is greater than negative absolute value of theta. So put theta 0 in. So this is 0. And also put theta 0 in. And this is 0. So this is going to tell us that limit of sine theta as x approaches to 0 from both sides is 0. And similarly, 1 minus cosine theta. 1 minus cosine theta is squeezed between absolute value of theta and negative absolute value of theta as well, similar to sine theta, okay? And then because of that, by squeeze theorem, the limit as x approaches to 0, 1 minus cosine theta is going to be 0 too. Okay, they didn't draw the graph of negative, let's say negative absolute value of theta here. Okay, this is absolute value of theta, this is negative absolute value of theta. They should have a picture here too, since they didn't have enough room, they didn't put it in here. Alright, so, but you can say that 1 minus cosine theta is between 0 and this, so this is good enough. You don't need another function. Alright, so let's take a little bit break here.